Welcome to this explainer. Today, we're diving into the ultimate cosmic detective story, the true nature of gravity. I mean, think about it. It's the force that literally dictates the architecture of the entire cosmos. It holds planets in orbit, it steers whole galaxies, and it keeps our feet planted firmly on the ground. And yet, for centuries, its fundamental mechanism was completely, utterly misunderstood. So, why does an apple actually fall? We take it for granted every single day, right? You drop your keys, they hit the floor. But if you really stop to think about it, it's bizarre. What is actually happening when an object drops to the ground? Why does a totally inanimate lump of mass just inherently possess this universal power to attract other mass? Well, to answer that, we've got to look past the surface of our daily lives, ignore what our eyes seem to be telling us, and completely shatter our assumptions about reality. All right, let's kick things off with Section 1, the illusion of pull.
For the longest time, humanity thought of gravity as a literal physical pull. Heavy things just naturally wanted to seek the ground. Then, Sir Isaac Newton comes along and gives us this incredible mathematical framework. He proposed this elegant, invisible pulling force connecting the apple to the Earth and the Earth to the moon. But the puzzle was kind of incomplete. Actually, Newton himself was deeply disturbed by his own theory. He famously called it spooky action at a distance. I mean, how could the sun reach across millions of kilometers of dead, empty space and instantly pull the Earth without any physical connection? Plus, Newton's perfect equations just couldn't explain the strange shifting orbit of the planet Mercury. Something fundamental was definitely missing.
Our journey today tracks this massive evolution in human thought. We're starting with Newton in the 17th century, shifting paradigms entirely with Einstein in the early 1900s, and then diving into the really intense, groundbreaking mid-century math that ultimately proved the darkest extremes of our universe. Moving right along to Section 2, Einstein's thought experiments.
You know, Albert Einstein proved that world-shattering ideas really don't require giant, multi-million-dollar laboratories. He famously pointed out that imagining something is often way more important than just memorizing facts. His biggest breakthroughs didn't start with pages of complex equations. They started with pure curiosity. Just picture him, a quiet Swiss patent clerk sitting at his desk, relying on incredibly simple thought experiments. He'd ask himself wild questions like, hey, what would the world look like if I could ride a beam of light? And from that single spark of imagination, the rigid ideas of absolute space and absolute time began to just crumble.
Now, this might sound like abstract, high-level philosophy, but it actually affects you right now, today. Because of Einstein, we know time is flexible. It ticks slower the faster you move, and it ticks slower the closer you are to a massive body, like the Earth. Think about the GPS satellites up in orbit. They're moving fast, and they're farther away from Earth's gravity. If programmers didn't account for Einstein's time dilation, your smartphone's maps would literally miss your location by several kilometers. Every time you navigate to a coffee shop, you are relying on the absolute fact that relativity is real. This brings us to the core revelation. Section 3, the fabric of spacetime. Einstein realized that space is not just some empty, silent stage where things happen to exist. Not at all. Instead, space and time are woven together into a dynamic, four-dimensional fabric called spacetime. And this fabric, it actively responds to whatever is placed inside it. It bends, it stretches, it ripples, kind of like a giant trampoline. This is where we leave the whole invisible pole idea behind forever and step into a universe governed by pure geometry. So here's the ultimate paradigm shift. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. Let's rethink what you physically feel as weight right now. Under Newton, you feel heavy because Earth is pulling you down. But with Einstein's truth, left to its own devices, your body just naturally wants to free fall along the curved geometry created by the Earth. What you actually feel as weight isn't a downward pull at all. It's literally just the floor pushing up and physically obstructing your natural free fall. Mind-blowing, right? Weightlessness is actually your natural motion. Weight is just the ground getting in your way. Okay, so what actually causes this fabric to bend in the first place? Well, it's not just solid stuff acting like a bowling ball on a mattress. Because of E equals mc squared, we know that mass is essentially just a super concentrated form of energy. Heat, pressure, momentum, they all contribute heavily to curving spacetime. Take your own body, for example. A massive chunk of your physical mass comes entirely from the frantic kinetic energy constantly binding quarks together deep inside your protons. It's this trapped energy, the furious motion and stress hidden inside objects that dictates the actual shape of reality. Which leads us straight into the dark stuff. Section 4, Singularities and Extreme Math. So what happens when this bending of space-time becomes, too intense? You get a singularity. Einstein's math predicted these terrifying, infinitely dense points where gravity is so unbelievably strong that the curvature of spacetime just becomes infinite. At a singularity, the classical laws of physics completely break down. They just cease to make sense. Now, initially, scientists hated this idea. They thought singularities were just flukes, errors in the math. The general consensus was, look, in the messy, real universe, matter is just going to swirl around chaotically, and it'll never perfectly collapse into a single impossible point. But it actually took one specific equation to prove they were a guaranteed feature of our universe. In 1955, a brilliant Indian theoretical physicist named Amol Kumar Raichachaudhuri created an equation that finally encoded the true dynamics of the universe. The genius of his approach? He didn't rely on assuming a perfectly symmetrical, uniform collapse like everyone else did, because perfect symmetry doesn't exist. Real stars are lumpy, they're spinning, they're uneven. Raichachaudhuri looked at how actual messy, chaotic flows of matter behave in spacetime, and that was the crucial missing link. To crack this, he broke down the incredibly heavy math of spacetime into 3 specific physical behaviors. Imagine a tightly packed bundle of light beams flowing together down a cosmic river. First, he calculated how these paths expand or contract as they move. Second, he looked at how the shape of this bundle gets distorted, stretching out into an oval, which physicists call shear. And third, he measured how the bundle twists and rotates, known as vorticity. By tracking just these 3 behaviors, expansion, shear, and rotation, he could map exactly where the entire universe was heading. The unavoidable conclusion of all this math became known as the focusing theorem. He basically proved that as long as you're dealing with normal matter, stuff that creates attractive gravity, and as long as rotation doesn't somehow overpower everything else, these flowing paths have absolutely no choice. It doesn't matter how asymmetrical or messy the collapse is, these paths must eventually crash together and focus at a single, infinitely dense point in a finite amount of time. This focusing theorem completely changed the landscape of modern cosmology. Standing directly on Raichaudhuri's geometric foundation, scientific giants Roger Penrose and Stephen Hawking developed their famous singularity theorems a decade later in 1965. Using that exact proof of inevitable focusing, Penrose formally proved that black hole singularities are completely unavoidable when a massive star collapses. Then, Hawking applied the exact same logic in reverse to prove the inevitability of the initial Big Bang singularity. These are monumental, Nobel-winning discoveries, and they all trace their roots back to Raichaudhuri's brilliant equation. And that brings us to our final act, Section 5, Why Energy Bends Reality. Look, at this point, we have pretty much conquered the mechanics. We know exactly how to calculate gravity. Just think about what we've achieved. We have literally photographed the dark shadows of supermassive black holes, millions of light years away. We've built giant detectors that physically feel the ripples of gravitational waves washing over Earth from distant cosmic collisions. We know that every single participant in the universe, down to the tiniest speck of dust, contributes to this massive shared geometry, and we can measure it with jaw-dropping precision. But before we wrap up this explainer, I want to leave you with the ultimate, profound mystery that still completely confounds our greatest scientists. We know exactly how energy curves spacetime, but why does it do so? Why did nature choose geometry as its fundamental language? Why does the trapped energy inside you demand that the 4-dimensional fabric of reality warp around your exact shape? That's the true beauty of the cosmos. Every brilliantly answered question just opens the door to a much deeper, far more magnificent mystery. So keep exploring and keep that curiosity alive.